marine biogeochemistry, and particularly in operational oceanography. Okay, so operational oceanography is like a weather forecast, but for the ocean. Okay, it's pretty new, but it's very important, especially if you work with people in ship or tourism or any kind related to biogeochemical problem or biological problem or ecosystem problem in the ocean. So this is the program that there was one. Yes, you know? Yes. Okay, so this part here, you should already do it with Professor Farnetti, and this is the part that we are going to start today, and we will bring us up to Christmas, more or less. Okay, so it will be a very short period, so quite tough for you, but also for me, because we also had some change related to the fact that you attended to the Python course, no? Yes. So first lecture should have been last Wednesday, but it was moved to on the 13th. So we will have lesson today, and then 3 times next week, 4 times the week later, and 2 times and twice the last week. Okay. Okay. So today we will try to make a little bit relaxing. So it will be an introduction, a very introductional talk about geophysical fluid dynamics, which actually is the new course, because up to last year the course was just fluid dynamics. Okay, so fluid dynamics actually is all this part, but the real part of fluid dynamics without any thank you very much, without any relationship with geo, and we will see what it means, have been done in the second part. Okay, so we will talk about rotating frame of reference. We will talk about the general introduction. Then we will introduce the rotation. We will look at the governing equation of GFD. We will then have some idea on geostrophy, barotropic waves, and finally we will talk about stratification when mixing. Okay. So I should ask you very briefly, just a few words, because it's very important for me, from which background you have. So you have a mathematician, physics, or if you have an idea in meteorology, atmosphere, and so on. Okay, please.
Bachelor's in physics.
Bachelor in physics. Okay, so you did already study something about fluid dynamics?
Not really.
Not really. Okay.
Master's in solid state physics.
In
solid state physics.
Solid state. Okay, so fluid dynamics, no fluid dynamics.
Master in meteorology.
Meteorology. Okay, so you are. You will come here. So. Physics, general physics, mathematics,
and BS in meteorology.
Meteorology, okay, you will come here.
Bachelor's in geophysics, master's in mathematics.
Geophysics, which branch? Solid. Okay.
BS in meteorology.
Okay, it will be the third.
Bachelor in physics.
Physics.
Meteorology.
Sorry?
Bachelor's in meteorology.
Meteorology, okay.
Geophysics.
Geophysics, which branch?
Seismology.
Seismology. Okay, so we have 4 people having some idea in meteorology. So in atmosphere, no one having any idea in ocean, but it's not so different. I mean, if you change the density, more or less things are quite similar. And other mathematician or some from solid earth. Okay, so let's start. So GFD, why GFD? So G stands for geophysical, F stands for fluid, and D stands for dynamics. So this, just switch. Okay, so this picture was taken maybe 10 years ago in Iceland. You know, Iceland is a very far Iceland in the north, close to Greenland, and which is one of my favorite places because it's very fresh. I don't like warm weather, and it's pretty nice because it shows you a lot of phenomena that actually are subject of GFD, and these high-level clouds, these low-level clouds. Then you have some, let's say, turbulence here, and then kind of, let's say, Okay, then we have the sun, of course, and some optical phenomena close the sun. Okay, so it's something that I like to show just to introduce the course. The second important thing that I want to suggest to you is the book. So my lectures are very, very basic, and they are, let's say, very, they follow very much this book here. Okay, so you can find these two books in the library. I think there are 2 or even 3 copies, but I will send you the PDF of this one, okay? Because I was able to take it 10 years ago, and I keep it very secretly, so keep it secret. But yes, because it was not the final edition. And it's very good, because at the end I will give you exactly the chapters and the section of each chapter where we did the lecture. Okay, so it will be like very easy to follow what is the general meaning of the course. Okay, so I like to make questions. So I hope you enjoy, even if also because we are just after lunch, so we have to be a little bit more energetic. And so, what GFD is going to study? Why GFD is going to study this, and how? Okay? So, first question, what? Please, according to you, even if you have already experience in meteorology, so you will be facilitated, but if you have an idea, what according to you, so you already had an idea of fluid dynamics, what do you think that GFD will going to study? Don't worry, I mean, there is no problem to make mistakes. Now you can make as many mistakes as you want. It's the real place to make mistakes. Please, come on. Don't be. Sorry?
The dynamic.
The dynamic. Yes, but think about the phenomena. So, what are the phenomena on our Earth that GFD is going to study?
Atmosphere and oceans.
Atmosphere and ocean. That is good. It's good, but it's not exactly a phenomena. So, you're right. I mean, we are on the right way. So, what are the phenomena? Flood? We can. It's. I will. Okay. Let me write them. Okay. So we say flood.
Please, can you on the line?
One.
Ocean current.
Ocean current.
Please, can you on the line?
Okay, so we can see.
Because sorry.
You cannot see it.
Ah, you're right.
Yes.
So earthquake. Earthquake.
Magma.
So what's the question again?
Magma.
Magma.
Sorry?
Yeah.
Barotrophic circulation.
Barotrophic circulation. What do you mean with barotrophic?
Okay, a circulation that is predominantly influenced by density changes.
Okay. Typhoon. Okay.
Then geostrophic flow.
Sorry?
Geostrophic flow.
Geostrophic flow. Maybe would be few people who know this. Coriolis. Coriolis is a phenomenon. It's a Coriolis force. Okay. Other?
El Niño Sofeonos.
El Niño. El Niño, you said.
Yeah.
So. ENSO, El Niño oscillation.
Eruption of the
Eruption of volcano.
volcano.
Volcano eruption. Okay, I think we are quite enough. Okay, let's keep them here. So, I will try to give some answer. So, among these, we are going to deal with fluid. Okay, so answer fluid, this is fluid, earthquake. Are they fluid?
No.
Okay, don't worry, I mean, who said earthquake? Don't have to blame it himself. I mean, it's part of the game, no? Magma. Well, magma is not bad. I will put a cross here. Barotropic circulation. Okay, circulation. I like circulation with fluid. Typhoon. Okay, it's fluid, geostrophic flows. Coriolis force. Coriolis force is a force, but can be related to some kind of phenomena, which are, for example, maybe you know cyclones.
Yeah.
And volcano eruption, I will put also across here, because volcano eruption can be considered as fluid, because we have, actually it's a two-phase fluid, because you have gas and solid, and sometimes also fluid. Okay, so here we can see three images. One is from mountains with some convection of clouds. This is a very, very small phenomenon of a drop going down in over a pond. And this is a vortex street near Canary Island from the satellite. So these are the Canary Islands, this is Africa. So you are from, most of you are from Africa, right? So, okay. So you are from Madagascar.
Yeah.
Madagascar, okay. Ghana, Nigeria, Ethiopia, okay. Iran, Nigeria, Madagascar, Pakistan, she's not here, and Nepal, okay. So Africa United, okay. No, different because last year we also had many people from South America or Caribbean, but many Cuban usually this time now. Okay. Good. Okay, so let's restrict now our analysis to these three. According to you, which are the phenomena which are going to be studied by geophysical fluid dynamics? Please remember this name, geophysical. Not just fluid dynamics, but geophysical. So we are dealing with something related to rotation and stratification. So rotation, because our Earth is rotating, and stratification, because usually we always have a field of density. Okay, so dense fluid below light fluid. So what do you think among these three? Which you will avoid, which you will not consider as GFD phenomena among these three? This one?
Yes.
This one?
No.
This is good, huh? We can keep. And this? Yes, okay, so we can actually, we can avoid these two. So actually this, you said, is in let's say on the threshold, okay? But this for sure not, because this is just a drop over a pond, or just a drop over a glass, okay? So it's too small in some sense to feel the rotation. Okay? So this is the first concept that's important for you to have today. The importance of GFD is that it must feel the rotation. So if we move to this picture, so this is another picture taken from satellite. You see how big Africa is.
Yeah.
Of course, yeah, you're right. What not? We are just small there, and so we are looking here a lot of different phenomena. We have cyclones, baroclinic cyclones here over the mid-latitude. We have intertropical convergence zone here. We have other phenomena in the southern Atlantic. We have some other very, very strong phenomena in the southern Atlantic, in the, let's say, Southern Ocean, let's say, and so on. Then we have other things here in the Northern Africa, and so on. Okay, so you said barotropic circulation, so we can say that we are very, very good with this. So when we look at the general circulation which act on our planet, it is from atmosphere or from the ocean. We can say that this is an important subject for GFD. Okay, so this is not a picture, of course. This is a simulation from a computer, from a numerical model, which shows you, let's say, the field of currents, sea currents in the ocean. Okay, so the velocity actually of the fluid of the in the ocean. And you can see again different kinds of phenomena. So you can see that there are some similarity. So there is an area in the tropics which shows something, there is some discontinuity. There are some phenomena which have some circular patterns, okay, which we will call eddies. Also here, and are very close to coast of the continents, okay, like from here, also here, okay. There is also one in the Mediterranean. So, if we look at these two phenomena, we can say that all the phenomena that act in the ocean or in the atmosphere are absolutely subject of GFD. But maybe I'm not totally correct, because not all the phenomena, as we will see, but many of them. Another thing that GFD studies, and that no one said, but it's good because we are here to learn, is climate. So climate is part of different, let's say, different reactions, different interactions among atmosphere, among ocean, among ice, cryosphere, and among biosphere. And you know that many people now talk about Anthropocene. So we are in the Anthropocene. So we are in the geological era where the people, men and women, acted in order to change, let's say, geologically our planet. Okay? Because since 200 years ago, we started to change the chemical composition of our atmosphere. And this created, as you know, a lot of problems. So this is one of the, let's say, most viewed images, which is the global surface temperature with 4 different independent records, which shows, of course, the long-term warming trends from the end of the last, let's say, 2 centuries ago, in the 19th century, up to more or less today. Okay? So, to study climate today, we need to create what we call the Earth system model. Okay? So, since we are going to study something which is not possible to measure, because we cannot make a laboratory experiment with our planet, even if we are actually doing it, because we are putting CO2 and other pollutants in our atmosphere, so we are actually making a global scale experiment. But in any case, our idea is to study, more or less. And to study it, it's important to put everything together. So what we call now the Earth system models. These are numerical models that try to put together ocean, atmosphere, biosphere, volcanic eruption as well, because if we want to study very, very long time scale, we need also to know the effect of the volcanic eruption, because volcanic eruption can actually have a big effect in the atmosphere, in the radiative properties of the atmosphere. But not just on the Earth, because GFD can be also used to study the circulation on rotating planets. Why not? So we said that GFD is a study of fluid dynamics on rotating planets with stratification, right? This is the 4 words: fluid dynamics, rotation, and stratification. Okay? So rotation and stratification make the word geophysical. So this is Jupiter. This is a very old, very old, not very old, but quite old picture that I used to show during my lecture up to a couple of years ago. And it's the famous great red spot on Jupiter, which actually is a GFD phenomenon. So you will see this is something which is rotating. So it's nothing more different from the other phenomena that we saw before. From here, for example, or from here. Okay? So another concept that we can consider is that we can also talk about similarity. And this is a characteristics that comes directly from fluid dynamics, because you can use fluid dynamics to study not just the fluid dynamics on the Earth, but also in the Earth. So if someone worked with the dynamo effect inside the planet Earth, the one which is going to create the magnetic field in our planet, that can be done with GFD. But also, as I said, we can study phenomena on other planets. So this is the Cassini spacecraft in 2000. This is a couple of years ago, 2017. The Juno cam from the Juno spacecraft, and you can see what beautiful and you can also appreciate the evolution from this picture and this picture. Okay, so you can see a lot of different phenomena which resembles the one that we have on our Earth. And there is even more another picture which shows you on the North Pole of Saturn in this case, thanks to again Cassini spacecraft in 2012. So you can see this sort of hexagonal pattern, okay, which is formed on the North Pole of Saturn. So there is here a link, but I will give you the PDF, the slide, so if you are interested. But this is very interesting in order to say that GFD is quite vast. Okay. Okay. Second question: why? Why we want to study GFD? So why we want to study ENSO, floods we see, ocean current, circulation, typhoon, cyclones, blah blah blah. Why?
Prediction.
You say?
Prediction.
Prediction. Okay. Prediction. So why you want to do prediction?
So early warning systems.
Sorry?
Develop early warning systems.
Okay, that's great. You said?
Prediction of what? When you said
Prediction of one of these means. So you want to predict typhoon, for example.
Oh, okay.
Why you want to predict typhoon? Great.
To know the physics behind anything.
To know the meaning.
To know the physics.
The physics. Yes. So it's, let's say, physics law. Then? It's pretty good. We have something more. So we have save life, but there is something more concrete. So, I mean, life is concrete. I don't want to say that. But, climate change, that's great. So, which is in some sense related to prediction but then, is there anything? Money. Because if we predict and save life, we can also save money for some reason. And we will see how. Okay, so first of all, we have Leonardo da Vinci, who you maybe know, who started to sketch some turbulent flow that he called. Okay? So looking at the swiveling motion of fluids, our ancestors were always curious, very interested, and they expressed a natural curiosity towards the fluids. So you remember that in the very early age of our civilization, we gave meanings to phenomena, to meteorological phenomena. So gods of thunder, gods of dawn, gods of the night, and stars. No, stars are not, but stars are also GFD. But all the meteorological gods of the ocean. Okay, so every civilization, every culture has given a specific meaning, let's say spiritual, something which is not physics, because at that period they didn't have the laws of mathematics and physics to explain this phenomenon. So the curiosity, and also the fact that in the past, many people, many artists also depicted different phenomena, like weather. So this is a picture of when Hannibal, who came from from the north of Africa, crossed the Alps to invade Rome in the ancient Roman Empire. This is the famous big wave from Okusai. So you know that if you think Okusai, you think, this is Japan. And if you think Japan, you think about? You say? Sorry? Asia, yes.
Earthquake.
Earthquake, tsunami, yes. So we can also put tsunami here. Which is a very interesting phenomenon because put together solid Earth and geophysics and fluid dynamics. Okay, and this is another interesting painting with a man possibly lost in the ocean in the Gulf Stream. Okay, with the sharks here. Okay, so why? You said very well. We want to save life. So we want to study GFD because we want to predict and to avoid that things like this will cause a lot of damage to people and to goods. Okay. So we want to create some early warning system. We want to have all the possible information to avoid that life will be lost, or also properties and goods and so on. Okay? But also you spoke about climate change, and also energy is very important because we can use the GFD equation to understand how winds, for example, work and how we can extract energy from wind. So these are some of the picture that I found in the internet on wind energy, and the wind energy is very important. We are talking about wind energy, but we also have tidal energy, and tides are other phenomena that are related with GFD. Okay, so someone said the Global Wind Energy Council, which is International Trade Association for the wind power industry, they say that 1/5 almost, 19% of the global electricity by 2030, so in 10 years from now, will be supplied by wind. Okay, so they said this in 2014. So if I will keep my course up to 2030, so for the next 10 years, I will go to see, okay, now we'll see if it's correct. Okay, then you talk climate change. Sure. So this was picture. So we are going to something which is more related to what we are working with, and you will work with in your diploma course, which is let's say temperature change, for example. So this is an example from NOAA, National Center for Environmental Information, which relates to 2016, so a few years ago, and we can see here in the year 2015, a general idea in the global of the area which were coldest than the average or warmest than the average. And you can see, of course, nothing new, that most of the planet is warming. There is something more which is related to prediction and to climate change, which is going to call climate service. So climate service. So services, climate service. When you think about, when you hear about this word services, means that someone is doing science also to make business. Okay. So in this particular case, there is a program in Europe which is called Copernicus. Maybe you know that. If you don't know, just Google and look copernicus.eu. So, and if you look to the climate service, climate.copernicus.eu, you will see that every month they deliver a bulletin. So they say, how was the climate? Let's say the climate, speaking about climate in a very short period of time is not very correct. But okay, how was the situation, let's say, in the past month? Okay, so I did it yesterday or the day before, and I took from this website this image, which is the surface and air temperature anomaly for October 2019, last year, relative to the October average for the period of 1981-2010. So, according to the average reference that we have in that period, which was based on ERA 5, don't think about it, ERA 5 is a dataset from ACMWF, we can see that this is the situation of the temperature, and this is the anomaly. And you can see, for example, all the Arctic and part of the Antarctic as having anomaly, positive anomaly of about 6 degrees. Okay, so we have something in Africa, for example, okay, with few, let's say, couple of degrees less in the Scandinavia and in the Western Canada and US. Okay, so this is a snapshot, a zoom on over the Europe. So this is the thing, and let's say one of the why, one of the reason why we use GFD. Okay, so to give services to people.
Sure.
Yeah.
I have a question on that diagram. If you look at around the poles, they usually record low temperatures.
You mean, you said,
I
sorry?
mean around the poles.
Around the?
Oh, the poles.
The pole, yeah.
Yes.
So here
why
and
is
here.
that they are recording higher temperature anomalies than the rest of the.
Yeah, yeah.
Why?
Well, this is very good question, and it's not easy to, to reply in very few words. But I think that the Arctic and Antarctic are the most sensitive areas in our planet. So if our planet has on the global have an average an increase of temperature of about 1 degree from the end of 19th century, Greenland had like 3.4 degrees. So, and Antarctica as well, especially this area here, which here is, let's say, negative anomaly, but it's just it's because there is a lot of ice melting here, so it's going to decrease for some reason, yes, the temperature. But the two poles are the area which are more sensitive, okay? Because of many, let's say, reasons that, okay, you will study that in the climate dynamics course, okay? But this is the idea. Okay, so why we want to stop? Because, okay, there is also another very important event which is called storm surge. So it's you were in Trieste last couple of weeks. You remember that there was very high water. Okay, the level of the sea level was quite high, and also in Venice. So that kind of phenomena are also related to storm surge. The fact that you have some atmospheric phenomena somewhere in the ocean, and their effect as let's say a gain of pressure differences is going to impact over the coast. Okay, so don't think too much about that, because you will see in the ocean dynamics course. But this is one of the things we want to defend our coast, especially for people who live close to the coast. And if you think, I think that 40% of the global population is close to the coast. Okay, so it's very important. And if you think also about the problem of the sea level rise, it's extremely important. And then, as I said before, it's important to avoid problem like that. So if you are able to give a good prediction to a ship, and you say to the ship where to go and try to avoid severe weather, you can avoid this, which is, of course, the insurance company are very happy for that. But of course, the people who are owner of this container are not. Then we have another very important thing, which is going very extremely severe, which is the pollution. So pollution is again close to the coast. So coasts are extremely important because you have the interaction of the land, of the anthroposphere, anthropic pressures, and of the ocean. And so it's a strong area of discontinuity where a lot of phenomena occurs. And so this is also in some sense related to floods, okay? Because when you have floods, you can have a lot of debris that go down through the river and then reach the sea. And finally, the problem of plastic. Okay, so if we are able to put together a little bit of chemistry within the GFD and study, for example, how plastic, which is a tracer, okay, so it's a tracer in a fluid, is moved from where it comes, and where it goes, following the currents and how it transforms. It's very important for now, but also for animals. So save life, yes, our life, but also animal life, because we are nothing without animal. Okay? Because if we disrupt, and we are already doing, ecosystem, animal ecosystem, especially ocean ecosystem, because ocean was able to reduce a lot of the CO2 put in the system by us. And when you breathe, if you take 2 breaths, one of these 2 breaths, the oxygen that you can take comes from the ocean. Okay? So if we live, if it's thanks to the ocean. So, and the fact that our planet is 70% water, well, we should think about why our planet is called Earth and not ocean, because it should be, because it's 70%, okay? Which is exactly the quantity of water that we have in our body. Okay? So it's something that we should think more about that often. Okay, final question. How we study all these things? Which are the tools that we use? You saw already something before. Models, that's great. Numerical models. Other? Satellite, very good. Something more?
Observation.
Observation, sure. We can put together with satellite. Something more? How we can study also? I mean, models is correct, but models are based on simulation, yes, but when I do a model, I mean a software, what I put inside? Data, yes, but how data are evolving? How can I evolve them? Equations. So mathematicians, help us, please, because we need you. Okay, especially to solve Navier-Stokes equation in big supercomputer. Okay, so we have 3 kinds of approach. We have a numerical model approach, an observational approach, and an analytic approach, because we can study numerical model. You can study GFD also by equation. Then we also have laboratory, okay, which is close to observation. Okay, so if we have a laboratory, we can also study phenomena. So have a look to some of these tools. So this is actually, these are 3 pictures taken by my colleagues. So this is our formed ship, research ship, which is called Explorer, and now is going to be retired because we have a new ship. This was in Antarctica, I think. And so with these kind of tools, you can observe, of course, the ocean, but also the atmosphere. Okay, so you just put some instrumentation like this. These are called float, Argo float. So Argo float are like big bottles, okay, with some sensor inside and an antenna, and they are put down from a ship. They go down, they drift. So they reach a parking depth in the ocean, they drift for 5 or 10 days, then they go deep, and then they go up, okay? Because they have special mechanism inside. They become lighter than the ocean surrounding them. And when they go up, they take all the measurement of temperature and salinity, of oxygen, whatever, okay? And then when they surface, they transmit all the data to the satellite. And we receive data in our laboratory, and we can use, as you said, the data to put within the model with the data simulation. Okay? This is another system. Do you know? Anyone know this?
Glider.
Glider. This is a glider which is, let's say, like a robot. Well, they are a robot. Both of them are robots. Okay? Then can be piloted, and then can be we can use them, and they also save money because a ship like this can cost 100,000 euro per month. Okay, even if it doesn't ship. I mean, is at port, so it's very, very expensive. And just one of these costs 200,000 euro, but you can use it many times. Okay, and it works 7 days over 7 days, 24 hours, doesn't need salary, doesn't need vacancy, food, whatever. Well, food, yes, needs to be recharged the battery. Okay, so we have satellite, very good. Then we have, anyone knows this? Radios. Okay, so in every airport of the world, we have someone like this man here. Someone, they are very old, no, you know. I know one of these, it was when I was in my Air Force. Very calm people, they go down, 4 days 4 times 4 days, they take the radiosonde and they put, and then they recover the data. But it's very important. Then we have things like this from the National Severe Storm Laboratory in the US, which are going to study tornadoes. And then we have also very big aircraft like this with a lot of instrumentation. So all these can be put together and create something which we call like global observing system. Okay, so satellite and observation come together, and they are taking all the data that are useful for us to study our phenomena. As I said, then we have also some laboratory. This is a naval engineering laboratory in the University of Naples. And then we have also analytic. So people who still work with pencil and paper, trying to solve or to improve the numerical methods. Because what do we do? Actually, we put our Navier-Stokes equation. You remember this? You already saw it in the Farnetti course. So we have the continuity equation and the momentum equation. We put this and we let do very big system like this. This is a Chinese supercomputer, and we hope that this guy here will give us very good projection, very good prediction, like weather forecast or projection for the climate. Okay, that is very difficult. You know, you will work if you are here. Possibly you will work a lot with models, so you will see, especially the one which will work with climate. So you will see that okay, it's something that is creating a totally new area of job. And someone also enjoyed very much to wear, you know, this man. So this was a visit of him at the MIT, and they gave him a T-shirt which say, and Moses said, with the Navier-Stokes equation, and the waters part. Okay? So it's nice. I mean, it's good that people like this go and take real contact with the people who work like you with science, okay, in particular with GFD. Okay, so this is another supercomputer. Another important thing is that we are going to create a lot of data. So if we are going to take big data from climate projection, for example, from weather forecast, from satellite, from observation, we are going to gather in a lot of data. And someone a few years ago already tried to estimate how much is the quantity of data that we are going to create. And if you look here, this is 2011, so almost we are 10 years from there. So we are order of petabyte. Okay, so petabyte is really, really a huge. So from 2010, we are expecting an increase of more than 300 times from the model, which is the yellow bar, and especially from the satellite or the radar. Okay, and it's incredible. Well, it's very interesting because he said that the volume of the worldwide climate data is expanding rapidly, creating challenges for both physical archiving and sharing. So this is not the first problem is where to put all this data, but also for ease of access. So how can I access to this data, and finding what's needed. So from all this huge quantity of data, can I find what I'm going to be interested in? And there is another important aspect that you may consider, the fact that now today we are not talking about flops, which is the floating point operation per second, but also IOPS, so input-output operation per second. And since you are going to increase the quantity of data, the amount of data, you will are going to increase also the quantity of IOPS. The problem is that, energetically speaking, when you compute something, you do like 1 picojoule. But if you move, when you do on your Linux MV, okay, you are requesting something which is 100 more than computing. Okay, so moving things, moving data is much more expensive than compute data. Okay, so something like this, only maybe 10 years ago, 15 years ago, was completely crazy. No one was thinking about it. But today, we are going to this level. Okay, so just to recap this very broad introduction. So, geophysical means rotation and stratification. Fluid, we are going to study the gas, especially in the atmosphere, and liquid in the ocean. Okay, that's why we are going to talk about fluid. And the word dynamics stands for the evolution of a fluid under the influence of body forces, like gravity, and surface forces, like friction. Okay? So all the phenomena that you can have in the atmosphere, or most of the phenomena that you can see in the atmosphere and in the ocean, of course, they are affected by this kind of force. And so we can say that GFD treats the physical aspect of the dynamics of fluids on Earth-like planets. That's why we call Earth-like, because we can also study Jupiter or Saturn or Mars or whatever. Okay? Also Mars, they are finding that there are a lot of phenomena, weather phenomena, which are very similar to our planet. Then, we found that GFD is mostly interested in large-scale motion, and we will see why. And then we also saw that there is this characteristic of similarity among the different systems. So, at the end, to the answer to the question what does GFD deal with? So we have atmosphere variability, like weather and climate, and ocean variability, like waves, eddies, currents, but also dynamo effect in the Earth interior, vortices on planet, and also convection and stars. Okay? Because also stars rotate and have fluids. What is important? Life, nature, energy, trades, and so on. How? Observation, mathematical physical description of phenomena by means of analytical theory, numerical models, and laboratory experiment. It's important that analytical theory and numerical models, of course, and most of all numerical models must be compared with measurements. So if I have a numerical model and make a simulation, I want to have a result, and I want to compare my result from the model to the observation in order to have the security, the safety. I want to express the uncertainty of my model. Okay, so if I make a forecast of temperature, I have to say what is the error. Okay, so numerical model must have the not numerical model, the scientists working with numerical models, they must consider also the error. Exactly when you have like a small ruler or any kind of instrument, equipment, laboratory equipment, and you have like the measure, you take the measure of this table, for example, and if you take the ruler, you will have that, you will make an error of few millimeters, okay? Same thing for our models. Okay, so we talk about scale, we talk about large-scale motion. The first very important definition that we must deal with is with the scales of motion. So you already have seen something about that. Is it maybe the one who make meteorology already saw something about that? So scales of motion are, let's say, numbers, dimensional quantities, which express the overall magnitude of the variables under consideration. Okay, so it's a very engineering approach, because we want to say how much is let's say the order of magnitude of a specific variable. So we will use I can leave this. We will use capital letters during all the course to express this scale of magnitude. In particular, we will use the capital L when we talk about length. Okay? So length in the ocean and length in the atmosphere. Capital T when we talk about time. Capital U when we talk about velocity. Capital rho, no capital, only rho 0, which is a Greek letter, when we talk about density. Delta rho when we talk about density variation. Very important, because we are talking about stratification, don't forget. Always, rotation and stratification, your best friend from now to the next year. And finally, capital H, when we consider the height where this density variation is acting. Okay? So if we take, for example, this picture here from satellite again, this was a hurricane during passage over Florida, 2004. So this part here, which is related to the diameter, we are going to take about, let's say, between 300 and 500 kilometers. Okay? So this is called, say, for example, L is 300 kilometers, about 3 degrees in latitude if we consider this. The time scale is about 2 days. So in 2 days, the, let's say, life of this phenomena is 2 days. So in 2 days, this phenomena comes from here, possibly, and then goes here. Okay? So 2 days we can express in second is about 2 multiplied by 10 to the 5. The velocity, it was a H5, class H5 of hurricane, 70 km per hour. Okay, with the top wind speed about 200 km per hour. Okay, so this is the sort of reasoning that you have to do when you approach to GFD phenomena. Okay, to first set the scale of motion. So how long, how much, how big, how deep, how much stratification is, how fast is. Okay, we can say, and we will see that how this changes, how this quantity changes. We can have a sort of simplification in our equation, which is extremely good when we want to solve our equation. Because since our equation that we saw here, so our equation have different terms. So we have the local variation, the advection, pressure gradient, dissipation. Okay, so if we are able to give numbers, scale of motion to each of these, we will see that if one or two terms are too big or too small with respect to other, we can neglect them. Okay? And so our equation can be easier to be solved. Okay. The third question, well, no, fourth question that today we want to think about is this one. So we talked about rotation and stratification, right? So these are two very, very important players in GFD. So the question is, at which scale the ambient rotation, what is the ambient rotation according to you? What is the ambient rotation? Yeah. Let's move to Coriolis a little bit later, but yes, is the rotation. So our Earth is rotating around the axis of rotation. Of course, our Earth is also rotating around the Sun. Just stop here because we can use other and go on very large scale in the unit, but this is more than enough. Okay, so the ambient rotation is this one. How much is the ambient rotation in the Earth? 24 hours. Okay, so this is a measure of time, not a measure in rotation. We will see very fast. Okay, so at which scales the ambient rotation becomes an important factor in controlling the fluid motion? So we saw at the beginning that if a drop is put in a glass of water or in a pond, according to you, does this drop feel the rotation of the Earth? No. But a cyclone? Do the cyclone? Yeah, of course. And the current, the ocean current?
It does.
Yeah.
What about the clouds over the mountains?
No.
It depends. But no is the most correct answer. Okay, so you have already some idea. So we can say that that's why we are talking about large scale. Okay? So large scale, we will have to quantify how large. The second question is, at which conditions the stratification effects have a dynamic role in fluid motion. So if I have, usually in the atmosphere and in the ocean, I have, like in normal condition, for example, let's say that this is a solid boundary, for example, the sea bottom or the land, okay? And this can be the sea water or the atmosphere, whatever. So we will see that naturally, a parcel which stays here will be denser than a parcel that will stay here, okay? So, and I can still move this, but I need something. I need, if I don't do nothing, like during fog condition, you have very still, very immobile air, also in the water, which is even more difficult because you have a lot of energy to spend. So if anything is done, it remains like this, and we call it the stratified, okay? Stratified flow. So if I put something like a current, so I'm trying to, for example, put a wind or a current, so I can hope that this system will start to move to create something. So the question is, how big should be this velocity, or how strong should be the stratification? How weak should be the stratification in order that the stratification itself will be broken by the velocity? And finally, what happens when we have a rotation and stratification? So let's start to put some number for these two questions. So we said the ambient rotation, we will call it with the capital letter, Greek capital letter omega, which as Chibueze said, is related to 24 hours. So we can say that our omega is 2 pi radians, because we are going to make one turn, over time of one revolution. Okay? So this will be 2 pi over 24 hours plus 2 pi over 1 year. Right? Because we are having the rotation related to a revolution and the rotation around the sun. Of course, this is much smaller than this one, right? Because if you take these numbers, you have 365 days here and just 1 day here, so this number is much smaller. But in any case, if we want to take everything, we have to take it. So this now we will simply call it 2 pi over the r, okay, where r stands for the rotation, okay? So omega, which is our ambient rotation, is defined as 2 pi over tr. We have a capital T, which is the time scale of our phenomenon. So now we have to, in some sense, compare the two, and we can define small Greek letter omega, which is the ratio between tr and t. Okay? We can also write it like 2 pi over omega over t, or 2 pi omega t. Okay? So, we said,
You said what is omega?
sorry?
You said what to call omega? You should call it.
This one?
Yeah.
We can call it omega for the moment. Let's say, because this is just we will find later that this has another name, okay? Maybe the one with meteorology background already discovered it. So we said before that cyclones are affected by rotation, ocean currents are affected, mountain clouds not so much, maybe not. So what is the similar thing among between cyclones and ocean currents, considering the time scale? So is this time scale of a cyclone larger than 24 hours or shorter? It is larger, because we said before, no, 2 days at least. In our at the mid-latitude, even a little bit more, even 3, 4, 5 days, according to the mid-latitude system. So for sure, so we can say that when t is larger or at least of the same order of tr, we have that the GFD phenomena is exactly GFD phenomena. So it's a GFD. Okay. So
I didn't understand why T is greater than TR.
why this?
T is greater than TR.
I'm not saying that why. I'm saying that if I'm just having a sort of intuitive approach, okay? So I said that cyclones are subject of GFD. So which is the time scale of cyclones? Is for sure larger than 24 hours. The evolution they have, so if I am fixed in one point, I'm seeing the cyclone coming, I'm seeing the maximum rain on my head, and then the cyclone leaving. So this period is more than 24 hours, okay? Because it can stay longer than 24 hours, okay? The same, the evolution of the system itself. So the cyclone starts to develop because of specific dynamics that you will see in the atmosphere dynamic course, and then evolve, and then dies. So his life is more than 24 hours. Good idea. Yes. No, it's okay.
I can't feel. You mean the tsunami is in the tsunami, the GFD is not okay?
Tsunami.
Yeah.
Tsunami is, let's say, it's very subtle subject, very specific, because it's a very fast wave. So actually, I don't think, well, they are, the trigger of tsunami is an earthquake, right? It's a subsurface, sub-bottom, sea-bottom earthquake. And the velocity that tsunami has can be so short, so large, that it can die in a very fast, very short period. Because if you have a tsunami very close to the coast, the tsunami completely disappears, obviously, creating a lot of destruction. But if you have other part of the tsunami which goes and can last for hours, but difficult, they last up to 1 day or 2 days. Because if you remember the famous tsunami in Sumatra, it takes like few hours, maybe even less, to reach Indonesia, and few hours to reach Sri Lanka, and few some hours to reach the Africa, Madagascar, Ethiopia, all the eastern part of the Africa. And I think that all the evolution, I'm not an expert in tsunami, but I think the all evolution is not so large than one day. So I don't think that this is satisfied for tsunami. Okay, maybe well, some tsunami maybe can last for long, but they goes like 200 kilometers per hour. I mean, the energy is transferred very, very, very fast. So that's why you give me the opportunity to leave it outside from our list. Okay, so I can also think about another thing. If I have the parcel which is traveling with a velocity u over a certain length L, okay? So this is just the evolution of the parcel with his time scale, like we said before with cyclone. Now we are thinking the parcel which is rotating, for example, in the cyclone, or a parcel which is moving in an ocean current, okay? Making some specific, traveling over some specific length. So we can define another number. So these are a dimensional number, okay? Because you are making the ratio between two times. So there is no unit of measure here. It's just a number, pure number. So another adimensional number, which we will call it epsilon, is again the time of revolution and the time taken by a parcel to travel over a distance L at a velocity u, which is a little bit different by this one, okay? So this is related more with the idea of advection, yes?
What's the time of revolution? Is time of revolution or time of rotation?
This is a good question. I don't remember exactly. Should be a revolution, I think. Revolution is, and the rotation is the, I don't remember from the astrophysics. You can Google it if you like, and you can maybe stop here. Now, it should be revolution around the sun and rotation. So this is because if you take the larger scale motion, we talk about revolution, which is one every 1 hour. But of course, what we need more, are more interested is the rotation, because, as you said, this is much larger than this one. Okay, so we will call it rotation, of course, because we will talk about rotation, not revolution. If you want to do revolution somewhere, we can do revolution for a better word, let's say. So let's use the word rotation. Okay, so time of rotation over the time scale that the parcel takes to travel over L at a velocity u. So we have again 2 pi over capital omega L over u, and we can have 2 pi u over omega L. Okay? So from this, we can also say that, so when we said that T should be larger than TR, it means that for GFD, okay, we have that omega should be smaller or order than 1, right? Because omega is TR over T. If TR is smaller than T, we have that this number is smaller than 1. So the smaller is this number, the larger will be the effect of the rotation over the phenomena. Okay? So if this number, if I'm having like T like 1 month, I'm very, very well affected by rotation, provided that we have phenomena that last for 1 month, which is possibly more probable in the ocean than in the atmosphere. Okay, in the atmosphere is much faster. So dissipation in the atmosphere is is strongest for some reason than in the ocean. Similar here. So if we want that GFD is okay, we have that this time scale will be larger than this one. So also epsilon should be smaller than 1. Okay? So the first question is at which scales blah blah blah. So the scales will be that when this is smaller than 1, we can solve this and say 2 pi u over omega L smaller or order than 1, which means u smaller than omega L over 2 pi or L larger than 2 pi u over omega. Okay? So I'm having a limit for velocity scale and length scale of phenomena which are affected by rotation. So I can have a maximum limit for the velocity and a minimum for the length. So over the Cushman book, you will find this table. And this is, let's say, very basic because we just, they just take this equation, this equation, very simple, and just put numbers. So from 1 meter to the Earth radius, which is the maximum length that we can have on our planet. And you can see that these are the limit of the velocity, okay? So, for example, 100 kilometers, we have less than 1 meter per second. 1,000 kilometers, we have 12 meters per second. Of course, this is a very, very strict approximation because you will see that we have, for example, in the example before, we had the cyclone which was between, let's say, in this length scale, because it was 300, 500 kilometers, and the velocity was 7 kilometers per hour, which is 20 meters per second, so it will be not exactly here, so it's more or less in this limit, okay? But still, this can help us, okay? So as we said, given L, rotation is important if U is smaller than L over TR, okay? L over TR, 2 pi over omega. So if we try to look at the phenomena and we start to give here, we are putting in practice the idea of scalar motion. So we are taking different phenomena, microturbulence, thunderstorm, sea breeze, tornado, hurricane, mountain waves, weather pattern, prevailing winds and climatic variation in the atmosphere. Again, microturbulence, internal waves, tides, coastal upwelling, fronts, eddies, major current, large-scale gyres. These words here, is something new for you? Is something that you have never heard about? About words, what kind of word you never about?
Large-scale gyres.
Gyres, okay.
Yes,
Others?
Microturbulence.
Microturbulence, okay. For you is fine?
Internal wave.
Internal waves, okay.
Coastal upwelling.
Coastal upwelling, good.
Sea breeze.
Sea breeze, okay. Okay, so sea breeze is the wind which goes on which flows over the land due to the change in pressure, difference pressure between land and ocean. For example, during the daytime. So during the day you have you have sun which heats the sea differently from the land, and in the night you have the opposite. Okay, so the breeze is exactly given by the fact that you have two masses, one water and one solid, which is heated differently because of their heat capacity. And so you have an establishment of a pressure gradient and you have a wind. That's all. So it's very typical in summer or in wind or in spring if you have very calm weather condition. Then the other problem was internal waves. So internal waves are waves. Well, waves is okay. Which are created when from a stratified flow I have some sort of very small perturbation. So I have a parcel which goes like this and then goes like this. Okay, so I have very small amplitude wave within the stratified flow. Okay, so these internal waves as something which occur almost everywhere, especially in the ocean, and have this kind of you see very small line scale. So minutes to hours. Sea breeze, we have 6 hours, okay? Then gyres. Gyres are like cyclones, more or less, but in the ocean. So are very big phenomena, like let's say larger than cyclone, like the big gyres that are in the Pacific Ocean. So you have this permanent circulation. You see basin scale, time scale, decades. Like for example, the thermoalign circulation in the world. So you have the global thermoalign cell, which start from the from the Arctic, and goes down to Antarctic, and then flows to the Southern Ocean, then go to the Indian Ocean, and so on. And the Gulf Stream is part of this, and this takes 1,000 years. So if you start from the Greenland, and you are a parcel there, you will come back there after 1,000 years, more or less. Okay? In the Mediterranean, it's the same. We have not 1,000, but we have 100. Okay? So Mediterranean is closer, of course. So, but one parcel which enters from Gibraltar Strait between Morocco and Spain will take about 100 years to come back. Coastal upwelling. Coastal upwelling is a phenomenon. We will see it. Upwelling means when you have the water which comes up. Okay? For mass conservation usually. And microturbulence. Well, microturbulence is the micro, which means small, and turbulence. So you have all the phenomena which, like the drops we saw before. Okay? So all the things that are very small, and as you can see, have a very small scale, like less than 1 meter, 100 seconds. Okay? A few seconds in the atmosphere and a little bit faster. So, GFD, I made an error because the arrow should come later, but okay. So GFD starts from here, more or less, when we have time scale larger than days. Okay, so tornado, I'm sorry, not part of GFD. Tornado typhoon, you can say. Well, who said typhoon? You refer to tornado or to what?
No, I don't know the difference between them.
That's great. I like you. Okay, so typhoon. I like this. Yeah. Okay, very good. Now, typhoon. Well, tornadoes, no? It's the one we saw before. It's the one very famous in America. All the people lost a lot of money. Blah blah blah. These things like this. Okay. So it's very fast, rotating system, which occurs when you have very strong discontinuity in the atmosphere. Okay, very hot water and very cold water which interact among them. They are quite common also in our region, in Friuli over the plain. Typhoon is the name of tropical cyclones in Pacific. So they are called hurricane in the Atlantic, because they come from a god, name we said, god of destruction from some Caribbean culture, and they are called typhoon in the Pacific. So in the Japan, I think also in the Indian, I'm not really sure, and they have another name in Australia. So typhoon are okay, because typhoon we can also like tropical cyclone. We didn't have a tornado here. Okay, good. And then hurricane, mountain waves, blah, blah, blah. Ocean, microturbulence, no. Internal waves, no. Tides. Tides. We are, let's say, it's hours. We can have tides which stands like 12 hours, because we have the first harmonic of the tides. But they are still at the threshold, okay? But tides are very important because it's the only body force acting on the ocean. It's the only, due to the gravity with the sun. So it's extremely important as a driving force. And then, okay, we have coastal upwelling, which is actually when ocean start to go up, we see how near to the coast. Fronts are where we have very high discontinuity between two water masses. Eddies are like cyclones in the similar. Cyclone in the atmosphere or eddies are the same. And then we have major currents and large-scale gyres. And you can see that we start from several days up to decades and beyond. And one very interesting thing that you can notice is that all the velocities in the ocean are slightly lower than the velocity of the atmosphere. Okay, so we are almost finished.
So, I don't know what mountain wave is.
Moulton Waves is the first, one of the first pictures that I show you. Is when you have it's similar to coastal upwelling for some reason. This one. So it's the waves, cloudy waves. So waves, let's say clouds actually, which have a wavy pattern, which develops close to mountains. So if you have mountains, you have a current, a wind impinging over the mountain, you have the air must go up. So if there is a difference in humidity, you have the creation of clouds. And this usually takes few hours. Sometimes if you have a change during the day, it disappears. Okay, so let me just very fast try to answer to the second question, which is related to the stratification. So we will do a similar we have similar ideas. So we have, so when we talk about stratification, as I said before, we have a pattern like this. So naturally, dense fluid will stay here and lighter fluid will stand here. So if this this fluid, so be careful, I will use the word fluid and the word flow. Is it clear, this difference? So fluid is the matter, flow is when you have dynamic, okay, when you have velocity. So it's, you have that, of course, flow is composed by a fluid. So I can have gas and water, and I have gas flow or water flow. Okay, so this is a fluid. There is no flow for the moment. So I have that the background density, the reference density, mean density is ρ0, again, scale for density. And then I have that this parcel here will have density ρ0 at a certain time, and this will have ρ0 plus delta ρ. So delta ρ is the variation, okay? So it's a positive variation. I'm saying that this parcel here has a density which is slightly larger than this one, and of course stays below than the other one. So after some time, so this is the initial situation, the final situation, for some reason, there's something happened, some mixing, let's say. We have that this parcel here has been displaced here, and this parcel here has taken the place of the previous one. Okay? So we have the reverse situation. So of course, most of you already studied physics. So what happened from this situation to this situation? Say.
Density change.
Density change, okay? Think about energy.
Equilibrium has to be established.
Yes, after, for sure. We are in a situation of equilibrium. We broke the equilibrium, then we will come back again to the equilibrium. But from here to here, is there some energy?
Yes.
So, do you remember how you call the energy which is related to density? Please? Convection is another thing, but well, it's similar, we will see. energy. Physics class 1 maybe. If I say energy, you say which kind of energy? Potential, and the other is kinetic. That's great. So I change the potential energy, right? Thanks to some kinetic energy. So energy must be conserved. I must have something here, like a wind, a current, whatever, someone who goes there and put this block here and this block here. So I can express the variation in potential energy. Be careful, I will use the same letter, please forgive me, of the velocity, but well, in some reason we will have some problem, but okay, we will be, I mean, you are all smart and you will understand that. We can use also double W, but our professor said that never be slave of notation, okay? So you can use whatever. When you do the exam, you can use whatever, even P or whatever. You can use P. Okay, let's use P. Make revolution now.
Let's use U.
And because since we said that U is velocity. Okay, so variation of potential energy is difference between the potential energy in the final stage and the initial energy, potential energy in the initial stage. So the potential energy as the initial state. If I take a reference, so I consider the position here as 0 and the position here as h. Okay, h is the height scale. Okay, so the scale of the density variation. So at the final position, I will have that, which will be the, you remember the potential energy formula? G? MGH. MGH, right. So now we are going to do it per volume. Great. So, PF, I will have this boy here. We will have rho 0 plus delta rho as density, G, H. Right? And this here, we should be plus G, of course, 0. Okay, because here H is 0. Minus initial situation, this one here, rho 0, GH, plus rho 0 plus delta rho, G, multiplied by 0. Okay? Easy. So, of course, these two terms can be neglected. I just have to make the difference between this and this, and what I obtain is rho 0, sorry, rho 0, but delta rho GH. Okay? So this is the variation of potential energy which has impacted over this system thanks to a kinetic energy. So again, what is the formula for kinetic energy? Okay, so mv squared, we divide by v, so we will have rho 0, u squared, use u, otherwise we will make a problem. We can put also over 2, okay, because we are very specific now. Of course, this is just a number. It's not important for now, but we can keep it. Okay, so before we use a two-dimensional number, small omega and epsilon, to say to make our reasonment over the time scale. Now we can use another dimensional number, which we will call it sigma. Okay, another Greek letter. Which is actually k over delta u. So rho 0 u squared by 2 divided by delta rho gh. So this ratio here is a ratio between two energies. So these are going to tells us what is how stratification will affect the dynamic. So I can have three cases. I can have sigma order of 1, sigma much smaller than 1, or sigma much larger than 1. So now we have to say when, in these three cases, the stratification is important. So if I have a sigma order than 1, okay? So it means that if I want to change the stratification, because this is the energy potential, the potential energy, which is related to the density variation, which actually describes the stratification, because if I have delta rho equal to 0, I have no stratification, I have homogeneous flow. Okay, so if this is order than 1, if I want to change the stratification, so I want to change my potential energy, I have to give also kinetic energy on the same order. So stratification is very important. If I have sigma much smaller than 1, it means that the kinetic energy is much smaller than the potential energy. So it means that I cannot do nothing with my kinetic energy because the potential energy is so strong that it will be so difficult to do something like this, to change something like this, okay? Because I need much more energy to break the stratification. So stratification is important also here. The third case says to us that kinetic energy is much larger than stratification. Sorry, kinetic energy is much larger than potential energy. So the system which is going to destruct this stratification doesn't care about the stratification itself, because the energy which I'm giving to this system will be completely always mixed, because the stratification will be so small, then I will have so much energy that the system will be never stratified. Okay? So here, stratification is not important because I have a mixed system, and so I have a homogeneous density. So I can conclude that GFD is when sigma is smaller or at least order of 1. So now we can say that stratification, the GFD, so stratification and rotation are important when sigma is order than 1, when small omega is smaller or order of 1, and epsilon is smaller or order of 1. Okay?
Excuse me, I'm somehow confused for the potential energy with pressure.
With
the pressure.
the pressure,
Yeah.
we don't speak about pressure. We don't have any kind of problem with pressure in this moment. I've never talked about pressure.
I see the formula looks like the one for pressure.
Ah!
Yeah, log G.
Yeah, you're right. This is the hydrostatic pressure. Yeah, we will see. We will see. Now we are talking about just potential energy. No, you're right. You're totally right. Yes. It's similar. It's very similar. And we will see the hydrostatic pressure which is very related to potential energy, because actually it is potential energy.
In that case, the potential energy becomes potential energy per volume.
This is exactly what, because we did this.
So why we do not consider the final
State.
kinetic energy?
The final
Kinetic
kinetic. Well, we can consider that kinetic energy is constant. It's like a constant of our problem.
But there is the variation in density, so there must be change in kinetic energy.
Yes, you're right. And this is what you can have it here. So when you have the density that is very strong, or even here, you can even block the system. So you have that the flow can be, let's say, slowed by the stratification. Just keep it like a very intuitive, because we will give more in detail in the rest of the course about that. Okay, very last thing. So now we can cancel this.
So we have another class.
So, you have another class. Really, now? Oh, okay, sorry. I used to be, say stop.